All right, welcome back to this two-parter in implementing Egg Walker from scratch. So in the first part, we wrote a bunch of code, and here it all is now. So this doesn't look like much, but it lets us do collaborative editing and real-time collaborative editing too, using the Egg Walker algorithm. And what that really is we've got this sort of funky graph traversal function called checkout, and that's going to create a CRDT. So in checkout, we create a CRDT, and as we add everything into the CRDT, we sometimes need to retreat or advance to say, like, kind of to switch on and off operations to say, yeah, you're on now, then we can apply a change, then we turn it off again and apply some changes over here, and then turn everything back on again, and so on. And doing this will end up getting us the actual final result document state. And unlike a traditional CRDT, we've got this operation log, which just stores the original version of all of the changes. So if we go back to the CRDT that I wrote in, like, I guess 2 videos back now, we had all of these items. And so we built this CRDT document state from a series of these item objects. And each one of these has an ID as well as an origin left and origin right. And they will get placed into this document array in exactly the locations that they should end up in the final document. But in Egg Walker, we don't do that. We just have all of the inserts at their original position. So the original position on my computer, I type the letter F. So we count from cursor position 0 right at the start of the document up to like position 20, and that F goes there at position 20. And then when we want to actually find out what the document looks like, only then do we create one of these CRDT document objects with a list of CRDT items. And we use that to be able to create this document object, turn things on and off, finally apply every change one by one, and return the resulting document snapshot. And the CRDT object itself, this CRDT doc, gets thrown away. So every time we do a merge, we merge everything together, we figure out what the new document state can look like, and then we throw away the CRDT. We don't need it anymore. We just keep the document itself. And you might think this is pretty inefficient, right? Because we're building this entire CRDT object just to like maybe merge just one change, and then we throw the whole thing away. And you'd be absolutely right. So in this video, this time around, so I want to finish up all of this work. So there's a few things that we need to do. First of all, I want to attach it to the editor. So we built this like nice, simple little text editor last time, which lets us do like this. But this is something I built a while ago. I want to be able to have this working using the code we just wrote. So that's step 1. Step 2, I want to have some actual tests. So I want to make sure that the system works correctly and works correctly in every case, not just the ones that I think of testing. Step 3, I want to actually do a few optimisations. So right now we've got this checkout function, and all it does is it starts with an empty list, and then it produces this list completely from scratch. You know, this list, aka this document. So I'd like to have it so that this checkout function should, in theory, only do work proportional to the number of changes that have been merged in, not proportional to the size of the entire document so far. Because if my document contains 1 million items and I add 1 item, I shouldn't be doing 1 million units of work. I only want to be doing 1 unit of work to add that new item into the list. By the time we're done, this isn't going to be the world's fastest implementation of Egg Walker. So for the fastest implementation, you can have a little look at my library called Diamond Types. And this is a Rust library which implements Egg Walker in just an insanely efficient way. There's all sorts of optimizations that I've got in here, and I'll name a couple of them just so you know. But the core of this whole, like, you know, many thousand line long Rust project is just the code that we've written today. We've got an integrate function that tells us how to insert something and how to position it. And we have the ability in our checkout function to go through the graph one operation at a time, figure out what we need to retreat and what we need to advance, and then apply all of the changes, which produces a resulting document snapshot that we can return. So before I start anything else, I'm going to do a git status git init. We haven't made a git repository yet. So we don't want node modules, and we don't want any JavaScript files, which we're going to create some, but none of them need to be committed to the git repository. So that's looking good. Initial implementation. All right, so we've got a git repository with that code. The next thing I want to do is I want to add that editor. I think we've got enough code so far to be able to get an editor working. So let's just grab the, I made that CRDT from scratch. I would like the index.html. I want styles.css, and I want the editor.ts files. And let's see what we've got. So editor here expects a CIDT document class, and it's going to call that in a bunch of different ways. So that class, if you recall last time, let's grab that code base. So this CIDT document class is kind of a wrapper around my million little functions. I'm just going to copy and paste it in, and then we're going to fix it up to make sure it works with our new code. So a CIDT document has, well, it's not going to have an inner anymore. It's going to have an oplog, which is a oplog. And because our document is a text document, we're going to have an oplog with where every single item is a string. So let's do this. All right. So this dot oplog is going to equal create oplog. And in our reset function, we will just overwrite that in the same way. Insert, local insert, this dot inner. So that should be this dot oplog. When we insert stuff, remember that inner takes a list of items. So we're going to have to split up this text into a list of Unicode code points. What's it? Mad agent. A position and deletion length. To get the string, so there's a few different ways I could implement this. Let's just have our, for now, our get string function call checkout. So checkout on this dot oplog, and then join that array of characters into one string. When we merge, we also are going to have to call merge into. So that's almost the same. All right. Okay. I'm going to comment out all this stuff so we don't end up with a bunch of junk at the bottom of our editor. And otherwise, this is looking pretty good. So last time in index.html, I used script type equals module. And one downside of this is I needed to run a web server to be able to have the whole thing work. But I realized recently that Bun actually has a bundler built into it. So let's grab from bundle.js, and then we just need one JavaScript file. And then I need to build it. So I think it's bun build, help. There we go. So bun build, I want to build editor.ts because that's our kind of raw entry point. We'll out file equals bundle.js, target browser. So CIDT document comes from eggwalker.js. There we go. So we've got a 9 kilobyte file containing all of the code we've just written. And here it all is. So I'm pretty sure this should just work now, actually. Let's just open index.html and see if it works. So I can type here, and look at that, it works. So if I reset stuff, and I'm going to go AAA, BBB, and let's merge everything together. And exactly as we expected and hoped, both of our document states merge. Let's see if delete works. So if I delete, let's say I delete 2 A's, and here I'm going to delete the same A and one of the B's, and let's merge everything together. So that's all looking really good. All right, so I'm really happy with that. We've now got a real-time collaborative text editor. Well, it's not really real-time, but I've got a collaborative text editor that lets me collaboratively edit documents. And when we merge all of the changes, we end up with the same document state in 2 windows. So this is totally enough to be able to build the world's simplest real-time collaborative text editor. If instead of, needing to click these buttons, we take the new changes and we send them over the network, and we receive the changes over the network and apply them to our local state when we receive them. And that would totally work. So yeah, mission accomplished, right? And I'm really happy with that. So I'm just playing with it now. And in theory, this should be, from a user perspective, indistinguishable from like the Fugue Max implementation. So the CIDT equivalent in its ordering. Because we're using that integrate function here, and we copied and adapted this from the CIDT's raw integrate function. This function determines and specifies essentially the order that the items end up in the final document. And because this function is the same in both our Eggwalker implementation and in Fugue, then in theory, at least, from a user's perspective, they shouldn't even notice that we're using Eggwalker instead of Fugue. It is kind of Fugue behind the scenes. So just to help you understand exactly what's going on, I'm going to do one more little thing, which is to make it so that as we merge all of these changes, I don't know how useful this is, but it'll be interesting to see. Let's console.table the doc.items. So I'm printing out that I retreated something, and then I'm going to print out the items themselves. I'm just doing this. This is really just to understand the algorithm itself, so we can see it in action. So I'm going to uncomment this out. So right now we're creating two oplogs, oplog 1 and 2, with Seth and Alice, and I'm typing hi, and Alice is typing yo. I'm just going to take out some of these O's to make it a bit quicker, or show a bit less stuff. And then we're checking out oplog 2 and joining it and printing out the resulting document state. I'm going to add one. Oh, no, let's run this like how it is. So if I run it, this is what we see. So to start off with, here's our table of all of the events that have happened, or all the operations. So we've got yo, that's position 0 and 1, then hi at position 0, position 1. So Alice typed yo, and I typed hi, and here are the parents. So we can see that the H it sort of comes off the root, like it was typed into an empty document, and so was the Y. And then the O came after item 0, which is the Y, and the I came after item 2, which is the H just here. So we've got these kind of two branches coming down. Actually, I'll show you what the graph looks like in my little handy dandy thing here. Oops. So if I do the same thing, one user types hi, one user types yo, and then we're going to merge everything. So here is what the graph looks like, where we've got, like from the root, we come down hi, and we also come down yo. And what we expect the algorithm to do is go down one path. So apply, then retreat and retreat. And remember, this changes, this kind of like toggles the events off. So it turns off these inserts in a sense. And then we can come down here and we can do these inserts here. So hopefully, even though these operations are switched off, what this should do is, as we do these inserts, it'll still insert the yo at the correct locations relative to these other inserts that have already happened. Here we go. So here's our operations. So first of all, we're going to apply 0. So we're going to apply this insert of y. And here it is now. Item 0 has an origin left and origin right of -1, which makes sense because we're inserting into an empty document. So there's nothing to the left or the right. And it hasn't been deleted. And its current state is 0. And if you remember the numbers, which is totally arbitrary, 0 means that it's in the inserted state. So it's currently like it exists in the document. Then we apply 1. So I'm going to insert this O. And this comes after the Y. So here it is here. And we can see its origin left is 0. So here. And its origin right is also -1 because it comes, because the thing to the right of it is the end of the document. Then we're going to do these two retreat operations. So this is kind of toggling off both of these operations. And at first we see we're going to retreat item 1. So here's item 1 here. And its current state is now -1. And then we retreat 0. And its current state is -1 as well. So -1 means that these items are considered to be like not inserted yet. So they're turned off. They're invisible to parts of the algorithm. And then after that, we're going to apply item 2. So item 2 is this here, which is me typing in an H. So from Seth, we've got an H. So we apply item 2, and here it is inserted into the list here. Now, it's quite interesting. Notice that the origin left and origin right are both -1. So when I typed this H character, I was typing it into a document that was empty. So the origin left and origin right should be relative to what the document that I was actually in looks like. And this makes sense. The document's empty, so there's nothing to the left and there's nothing to the right. And we get these origin left and origin right of -1. It's interesting that the algorithm decided to insert it here at the end, which is the right behavior, because this item here, this H and this Y or whatever it was, these are two inserts at the same location and they were concurrent. So they happened at the same time, essentially. But the algorithm would have eventually fallen back on comparing our user agents to see which user agent had came earlier and later in the alphabet to decide the final order of these two inserts. So the H went here. And Fugue is designed to be, they call it non-interleaving. So if I type a bunch of stuff and you type a bunch of stuff, our keystrokes shouldn't end up, like our inserts shouldn't end up all gobbledygook kind of mudged together. Instead, we should have all of my, all of one of our words and then all of one of, the other person's words. And it's kind of arbitrary which way around those go. But the important thing is that everything you type and everything I type, if we type in the same location, they should end up like, as little blobs that aren't mixed together. And that's exactly what we see. So that was yo. So here's your O, and here's my H for my hi. And then I can apply finally my hi. So here's the I. And we can see the origin left of this one is 2, which is that there, which is exactly what we expect. And right now the hi is switched on. So because there was nothing else at the end, I mean, you might think, oh, well, at the end, surely then we turn on all of the operations and see what it looks like. But we don't actually need to do that. So we got to the end, and as we did all of this, we created the text document, which was yo hi in this case, and the function just returns. I'll show you what that looks like if we add. So let's just, after we've merged, I'm going to do another local insert into, let's say, upload 2 from Alice. Let's just say Alice types another thing right at the end. So right now we've got this document state, but if I just add an extra keystroke at the end, we end up with this down here. So we end up with one more event that comes after both of these paths. So this operation has a parent of this and a parent of this. So let's insert at position 0, 1, 2, 3. So that's at the end of the document, I think. So 0, what is it? So position 0, 0, 1, 2, 3, 4. So no, let's type it at position 4. And I'm going to put in X. I guess I could, just for consistency's sake. So if I put an X at the end, let's see how the algorithm changes with this additional insert. So the start of it's going to be exactly the same. So obviously we've got this additional event or operation right at the end here that's inserting at position 4. And it has parents of 1 and 3. So that's 1 and 3, exactly as we expect. So we apply yo, retreat. We apply hi, that's 2 and 3. And now this is when we stopped last time. And remember that the yo was in the current state of -1. So the yo is actually disabled. But now what I want to do, the next operation that we're going to apply is this X right at the end of the document. And because this X comes after both paths, we need both paths to be turned on to be able to actually figure out where position 4 is in the current document state. So the next thing the algorithm will do is do its advance operation. So we're going to advance 1. So this is turning this event back on again. And then we're going to advance 0. Oh, sorry, it's going to turn this insert back on and then turn this insert back on. And you might notice that these are in sometimes they'll be in a different order. The order doesn't actually matter here because remember, we're just turning switches. It doesn't really matter which order you flick a bunch of switches on a dashboard. So once they're both turned on, then finally we can apply number 4, which is going to be, as I said, that X here that comes after everything else. So with everything else turned on, we then do this. And because it was at position 4, it's quite simple for the algorithm. It's just like, well, the item directly to the left is item 3, which is here. There's nothing to the right, and it's not deleted, and its current state is in the enabled state, essentially. And that all works. So we get yo hi X, which is exactly what we expect. All right, so that's pretty good. It's pretty good, but it's not excellent. And we can make this excellent. But let's start with tests. The reason I want to start with tests is because this is testable already. And that way we can make sure that we can fix all the bugs now. And then as we make more changes, we can hopefully not introduce new bugs. But we'll have a testing suite to make sure that our code keeps on working as we improve it. So I'm going to make a new file called fuzzer.ts. I use the term fuzzer for this kind of testing. Some people call this property testing. I think of it this way because I'm using a randomizer. So I'm going to have a randomizer that's going to spit, vomit absolute rubbish into 3 different text documents all at once. And we're randomly going to decide, pick 2 pairs of text documents sometimes and say, you 2 merge, and they'll copy all of their operations that are missing in each other across. And once they've merged, we'll make sure that the resulting document state is exactly the same. So this is the convergence property. We know that anytime 2 peers trade all of their changes, they should both end up in the same state as a result. And if that's ever not true, then we know there's a bug and we'll go and fix it. So whenever I write code like this, there's a few things to bear in mind. The first one is that it's really important. So it would be tempting to use math.random. Math.random is totally fine for what we need, with one caveat, which is that math.random is not a seeded random number generator, which is to say that every time I call math.random, I'm going to get completely different random numbers. And I actually want to get the same sequence of random numbers this time. And the reason for that is that if my program crashes, I'd really like to be able to debug it. So if we use a seeded random number generator, then I can pick a seed right at the start of my program. And my program, even though it's like random, it's going to be the same random sequence every time we run it. And that way, if I run it and my program crashes, then I can add more debugging statements or, put print statements, whatever else I want, and then run it again. And it's going to crash in exactly the same place, in exactly the same way, which is really important and really helps a lot for debugging. So to that end, I'm going to add some stuff to our project. I'm going to use a library called seed-random and at types seed random. This contains TypeScript type definitions for this JavaScript library. So with that, let's write a fuzzer. I'm going to go through this reasonably quickly just because I've written these before. It's not a common programming practice. I think more people should write fuzzers. I think they're absolutely fantastic. They're so good. So import seed random from seed random. Sure. I'm also going to import assert from node : assert strict. Let's see if it's happy with me. It is not. Bun add types bun. Is that a thing? Hey, there we go. All right, great. So that gets an assert library. Assert contains a whole bunch of deeper quality checks and everything else, so we can make sure our code works right. So I'm going to use the that wrapper, this CRDT document wrapper that we made already, this thing. But let's start with the actual fuzzer, the kind of body of the fuzzer. So function fuzzer, this is going to take a seed, and if I ever call it with the same seed, we should get exactly the same behavior out of our fuzzer. So const random equals seed random. So that's going to get us a random number generator. And let's just test it. So console log random, and we'll spit out some random number generators. Fuzzer 2. So let's run our fuzzer with a seed of 2. Run fuzzer. And if I run it again, this is exactly what I want. So I'm going to copy in a few helpful little testing functions. So randint is going to return an integer up to n, so from 0 to n. And randbool is going to return a float with some weighting of weight, I guess. So if weight was 1, it'll always be true. If weight is 0, it'll always be false. And if weight is say 0.1, then my randbool function will return true 10% of the time. Next, I want to create some documents. So I'm going to make 3 documents. There's a thing with real-time collaborative editing where it turns out you get basically all of the benefits of fuzzing from 3 peers. 2 is not enough, 3 is enough, and 4 is kind of redundant. I've never ever gone from 3 to 4 and found any new bugs. And I've made probably 30 of these at this point. So I always use 3 documents. It's the right number. So let's see if we can get away with this. So new CRDT document, and our user agent is A, B, and C. So that'll be nice and easy. Now, the loop of this, so these documents start off totally empty. And what we want to do is loop. So for let I is 0, I smaller than 100, I plus plus. 100 is kind of a nice number. And 100 times, I'm going to make some random changes to one of the documents, first of all. Then I'm going to consider picking 2 documents and merging them together and checking to make sure that when I merge them together, I get the resulting document state, the document state that I expect. So let's do that. So first of all, let's generate, say, let's edit 3 documents. So for let I equals 0, D equals 0, D is less than 3, D plus plus. So we'll pick a random document. So document D, const doc equals docs D. Then const len. So what I want to say here is I want to grab the document's length because I'm going to insert or delete something somewhere in the document. Before I do this, I am going to actually make that change I thought about doing earlier of having it so that our document stores. So let's do it like this. Stores a snapshot, which is the list of strings, so the list of items that we have in our document. this dot snapshot equals empty list. Get string then. Instead of doing a checkout, we can just return this dot snapshot dot join. And then there's a bunch of times that we're going to have to regenerate this snapshot. So every time I merge the changes from another peer, I'm going to have to say this dot snapshot equals checkout this dot oplog. So obviously this is going to regenerate the snapshot from scratch, but soon I want to make it so that it doesn't, and it does something more efficient. Likewise, in the insert function and the delete function, we can do this, but there's a little trick here, which is that because I know that this insert happens at the current point in time, I can actually just do this. Const inserted equals that. So I'm going to tell the operation log about this insert, but I can also just edit the snapshot directly without having to regenerate it from scratch. So this dot snapshot dot splice, splice at some position, so pos, then the number of, how does splice work? Start, delete count, and then all of the items that I want to insert. So I want to delete nothing, and I want insert inserted. Does this, there we go. So if we actually look at splice, we insert a list of items at the end, and that's all the items that will get inserted into the snapshot at that location. And likewise for delete, I can do the same trick. So this dot snapshot dot splice at position del len, and that'll delete all of the items directly in the snapshot. Oh, and finally reset should be this dot snapshot equals an empty list. Great. So I did all of that, not because we actually really needed to, but because I want to be able to use this snapshot from the fuzzer. All right, so back in our fuzzer, we've got this little loop here, and this inner loop wants to say 3 times every iteration, pick a random document, which I'm not actually doing here, and then make a random change to that document. So let's have a function to like get us a random document. Const rand doc equals, it's going to be docs at rand int 3. So rand int is going to return a number up to 3, so 0, 1, or 2, and we'll just grab doc, whatever that is. And that should be a CRDT document. So the document I'm editing is a random doc. The length of that document is doc.snapshot.length. So I want to either insert or delete something. If the document's empty, I'm obviously going to have to insert something. So I guess weight equals, if len is equal to 0, then the weight is 100. Otherwise, the weight is, say, 0.5. I'm actually going to do something a little bit trickier here. I'm going to try and just sort of have my elbow on the scale of this so that, let's say our target length for the document is, well, let's say we want the document to be about 100 characters in length. Then what I can do here is say, maybe this is too fancy. If the length is less than 100, then we're probably going to add something. So let's add something with a probability of 0.65. But if the length is more than 100 or more, then let's only insert something with a probability of 0.35. So we're going to lean towards deletes once the document's that long. And yeah, and doing these little tweaks, I don't know how much difference they actually make in practice. It's hard to tell sometimes. I think fuzzers are as much of an art as a science. And part of the reason for that is that it's very easy for the program to spend a lot of time while it's running the fuzzer doing something that you know works really well and then not actually get to the good stuff. So there's a whole lot of small little choices I make while I do this, like starting from an empty document, then just doing 100 changes, because that'll just make 100 operations. And remember, our algorithm right now is n squared. So if this did say many, many operations, it's going to take a really long time to run as the document gets bigger. Instead, I'll just run 100 iterations, and then I'm going to run the fuzzer itself in another loop. So we'll just try out a whole lot of different seeds. And with each seed, we'll start from fresh documents. And that way we can make a whole lot of progress trying a whole lot of stuff. But 100 is still enough that we're going to see some interesting behavior. So everything that every weird combination of operations, it'll almost definitely shake out with 100 items, 100 edits. I mean, probably 20 or 50 would be fine too if we wanted to make it run even faster. So if the length is 0, or rand bool. So so this is like the insert weight. Insert weight. Then we want to insert. Else we'll delete. So let's pick something random to insert. So let's have a little alphabet. So alphabet's going to be A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. There we go. So that's our alphabet. Rand character equals rand int alphabet dot length, and our alphabet at that. And I'm also going to make this into a list from a string. The reason why I like making things into a list like this is because that way, if we wanted to, we could actually test this out by putting some weird emojis and stuff in here. And those emojis should be treated correctly by the algorithm. But I'm probably not actually going to test that here. I think I'm happy with this. Oh, and let's also put some spaces in there. So now we're going to say const content equals, let's just insert one thing. Rand char. Const pos is going to be a random integer. So we could insert at position 0 or anywhere up to like after the last character. So the position then should be rand int len plus 1, and that'll do me. So doc dot insert at position content. Yeah, great. All right. And for deletes, we want to do a similar thing. So const pos, except this time it's rand int. It's just len because I have to delete something in front of the position. And we could even as well, if we want const del len, pick a random length so we can delete multiple characters. And we could be doing the same thing here and inserting multiple characters all at once. That's generally a good thing to do because runs are very common by users, and there's a lot of optimizations you often want to make that take advantage of runs of inserts to be able to make it faster. But in this case, we're not taking advantage of that at all, so it doesn't really matter at all. But whatever, I think this is fun. So the deletion length is a rand int. Well, we don't want to go past the end of the document. So the maximum it could be is len minus pos, but that means that like a lot of the time we're going to be deleting giant swathes of the document whenever we do this delete. So let's just take the math.min of that and, I don't know, 3. So the maximum length that we're going to delete is 3 items. And then doc.del at position, the deletion length. Great. Oh, I'm going to add one more thing, which is just a little check function. So here in my CRDT document class, I'm going to add a function called check. And all this is going to do is make sure that our snapshot matches what we expect. Yeah. Const actual doc equals check out this.plug. If actual doc, I want to say like if the actual document does not equal this.snapshot, then throw error invalid document out of sync. But unfortunately, I can't directly compare arrays like this. So I'm going to be a bit sloppy and just join and join. So this way I'm generating a string and I'm generating another string, and we'll just make sure that both of those are the same. And for now, let's do that check every single time we add something. So doc.check. Over time, once we're more and more happy with this and the fuzzer working correctly, I'll probably comment this out because it's going to take a bunch of time every time we go through. And I want the fuzzer to be kind of efficient with my CPU cycles. It should be really exercising and really hammering our library. If it's just running some checking function over and over again with most of my CPU cycles, then we're not going to be able to actually test the algorithm very well. But on the flip side, if we run the fuzzer and it finds a problem, I want my fuzzer to crash as soon as humanly possible, or as soon as computationally possible. Because the earlier it crashes once something goes wrong, the easier it's going to be to find and debug our algorithm. So that's always the trade-off. All right, so we've gone through, we've 3 times added made 3 random changes to some documents. Then next, I'm going to pick 2 documents and merge them. So doc A equals rand doc, const B equals rand doc. If A is equal to B, then let's just ignore it. So you get a by this time if we happen to pick the same document twice. That's fine. Now what I want to do is merge them. So A dot merge from B, B dot merge from A, and then we need to check to make sure they've got the same content as a result. So assert dot deep equal. So deep equal is going to kind of look inside things, and I want to assert that A dot snapshot is the same as B dot snapshot after I've done the merging. Since this merge function is going to also update the snapshot based on a checkout. Okay, so that's a fuzzer. And I hope that doesn't seem too complicated. We've only got like, 50 lines or so of actual fuzzing code. But this one thing alone, it's utterly insane the number of bugs you can find with some code like this. Like the number of bugs found per line of testing code from a fuzzer is far in excess of anything I've ever done before. Like it's absolutely wild. But the real question is, do you think it's going to run first time? And I can't tell. I've worked from a reference, so theoretically it should all work, right? But if there's any single little problem in there, anywhere at all, it's going to crash horribly. And my prediction is I've made at least one mistake. So let's see. Oi, I think it might be working. So I'm going to kill it, and let's get rid of console.table. Oh yeah, all of this stuff. There we go. So that's looking pretty good. And let's get rid of the console.logs as well. All right, so that ran correctly. So it ran, it's just printing stuff out from here. It ran, it did 100 iterations, and then it finished. And that's working. So to test it properly, I'd actually do something like this. For let I equals 0 or I smaller than 1,000, I++. And every time through, let's just run the fuzzer using I as the seed. Let's print out seed I. It's often good to print out the seed because if it actually crashes, then I don't want to have to, like, let's say I leave it for an hour and then it crashes. I really want to know which seed it was that made it crash. So that way I could just run, I can comment this out and be like, it was that seed that crashed it. And that way this will crash almost instantly without me having to wait for an hour to run it. So it's working, which is really cool. We can even, at the end, let's just for fun, console log docs 0 dot, was it toString? Yeah, get string. Let's see what our documents end up as. So there we go. That's one document, and here's some more. And as I say, in theory, if I kill it and run it again, we should end up getting those exact same documents because our system is deterministic, completely deterministic. All right, so I'm pretty happy with all of that. Let's get rid of that, and I'm gonna git status, all of this stuff. Added browser. Oh, actually, one last thing I'm gonna do. I had that wild command that was like bun build, all of this crap. I'm gonna add this as a build command. Oh. I'm gonna add this as a build command. So let's go back here and go to our package.json and add something called scripts. And I want to build script, which is gonna, run all of that. So now I can actually just go bun run build, and it'll run that command line for us. So like bun is running itself in turn, but that'll end up meaning that I don't have to remember any of this stuff. If I run bun run build, it's going to automatically redo it for me. So also it means that other people don't have to guess what random command line is going to actually make the thing work, especially since the bundle itself isn't being checked into Git. So git commit, added fuzzer and browser stuff, browser editor stuff. Oh, one other thing I forgot about. This still says nano fugue max. This is like egg walker. Like egg walker from scratch. Very important. Changed title. And now here is our new one. So I'm going to refresh it. So this is egg walker from scratch. And it all works. Hey, cool. I'm really happy with that. Oh, I also promised one last bit of debugging fun, which is showing those actual graphs. I'm not going to rewrite this code from scratch. I'm not going to do it live in front of you. I'm just going to copy it from what I prepared earlier. So I've got my nano egg walker, and in here I've got this thing called dot.ts. I'm going to copy that in. So dot is part of a software package called GraphViz. And if you want to, you can look online. GraphViz is a tool that can output diagrams like this, including the ones that I'm doing, from some text. So you write a whole bunch of text describing a bunch of nodes and their interconnectedness, and it'll spit out an SVG that looks like this. So you can get it to generate an SVG containing all of the, everything that you've got. What this code does is it actually generates programmatically like one of these dot input files. So I'm creating this lines thing, and at the end I join all of the lines together with the new line, and we take this entire string that it generates and spit it into dot, and dot then can produce an SVG file containing a beautiful diagram with the graph. So there's a couple ways that we could make this work. So someone took GraphViz and they compiled it to WebAssembly. So we can actually just use a direct version of dot as a WebAssembly module. So bun install this thing. So hpcc-js/wasm-graphviz. This is the package itself. So what we want to do is this, import from this thing. There's something called GraphViz. I'll fix all of this stuff up in a minute. What I can do then is say async function gen svg, say, which will take in an oplog. And we're going to actually, let's say we want to output it out file string. So we'll load GraphViz, and then so we can grab the dot source by calling the function that's above, which generates the source. And then all we need to do is call graphviz.dot, and this is going to return the SVG. So let's just output it like that for now. Need to export that. Gen SVG from oplog2, and we should be able to see the SVG that it creates. Also need to fix all these problems. So we need to actually export some of these types. So let's export type LV. I'm going to export type op, and I'm going to export type oplog. And hopefully, yeah, great. So that fixed all of our problems. Looks like we don't actually need op after all. So if I bun run, what was it, egg walker? Hey, now we get an SVG coming out. And if I put this into an SVG file, I should be able to see the graph that we generated. So I'm going to do it the slow way. pb paste at out.svg. And I open, out.svg. And there we go. So here's the graph that we actually generated. And as you can tell, this looks the same as what I'm generating on that website because it is literally the same code. But this is the actual graph that we were generating in our testing code. So right down the bottom here, this is this oplog here. So yeah, so that's pretty cool. I'm going to add this to the Git repository, but I'm actually going to comment it out because I don't want it to be pulled into the browser bundle just here. Oh, I don't know. Let's actually fix this up. So let's give this function say file name is a string. File name is a string. Const svg equals that thing we had before, and then we're going to write the svg out to the file name that you pass. So this file here, this fs implementation, this won't work inside a web browser. And I commented all this stuff out because none of it worked inside a web browser, but we can pull it in bun. So import fs from node fs. So gen svg blah.svg. And if I run that, here's my blah.svg file as expected. So that's all working. So we added dot output via graph viz. All right. So there's one last thing that I want to do, which is I want to be able to make this implementation work a bit better. There's a few things I hate about it right now. I hate that it's an ON squared algorithm. So ideally it should be ON or ON log n. And I'm not going to get all the way there today, but I'm going to at least improve the worst parts. When people first encounter Eggwalker, I've had a few people who, are kind of like very switched on, ask the question of, well, how could you make it work fast? Because surely this diff function has to be very, very slow, since it's got to do work like this. And the trick is that there's a way to write this diff function, which is going to actually be very efficient. Now, remember that most of the time, version A and version B are very close together in time. So if I've got a really big document with lots of stuff, and then I have some tiny little change at the end. So we've got all of this stuff, and then right at the end, I've got this little bubble. Most of the time, it's going to look like this, where I'm going to be asking for what's the difference between, say, the parent of this change, which is version 33, and the version after this has been applied, so 34. So I'll be saying the difference between 33 and 34. And what I want is I want the algorithm to start at the bottom and just go up the graph until we find something which is common. So once we reach this 33, if we're looking at the difference between 33 and 33, it's going to be nothing. So the way we can solve this, or the way that we can implement this efficiently, is by using a priority queue. So first of all, I'm going to delete this horrible diff function. I hate it. Oh, let's just comment it out. But I hate it, and it needs to burn and die within fire. All right, so the way I want this diff function to work is I'm going to use a priority queue. And every time, what we're going to do is we're going to put all of the put operations or put local versions inside our priority queue and pop them off. And whenever we sort of pop off the next one, I'm always going to look at the item with the highest local version, because I know that, it's going to end up getting me the right result. So let me show you what this looks like. So function diff, this is our new better diff. I'm going to take an oplog. In fact, it's going to have exactly the same signature as the old function. I'm also going to need a library. So I'm going to need a priority queue library. Unfortunately, one of JavaScript's many flaws is that it doesn't have a priority queue built in. Rust does, which is why Rust is the right language for me. Also, for what it's worth, I know lots of people on Hacker News complain bitterly about leak code problems, but this is the sort of thing where if you don't know algorithms and data structures, you can't actually optimize algorithms like this. I know that most people don't write code like this, but this stuff's super important and super useful. I think priority queues are one of these tools that you reach for so often when implementing complex data structures and complex algorithms. So I've done some searching and I found a good priority queue, or a reasonable priority queue implementation in Node.js. So let's just add something called priority queue.js, and I'm also going to add type/priority queue.js, which is again some TypeScript types for it, so that way we can get auto completion and TypeScript isn't mad at us. So what I want is a queue. So const queue equals new priority queue, and it's going to be a priority queue of local versions. So everything inside this queue is a local version. It's a number. By default, a priority queue, this is a max heap, which is to say every time I pop items off it, I'm going to get the largest item. So let's just look at what that looks like. Bun REPL and queue.enc, I think it's enq 3, 6, and 2. And then when I go queue.dequeue, so that is pop a thing off, first of all I get the highest thing, then the next highest, then the next highest, and then after that it crashes because there's nothing in it. So this is going to work out pretty well to be something that we can add all of our local versions in, and then when we pop them all off, we're going to get them off in the order of the highest local version downwards, which is what I want. I'm also going to do something a bit funny. Const enum, I'm going to make this sort of diff flag enum. So I've got A, B, and shared. So the idea is that I've got this list of A's and I've got this list of B's, or B local versions. And I think of it sort of like a coloring problem. So if I'm trying to find the difference, say, between this and this, then this is colored with I don't know, green or something. It's got the, because it's only in A. And this is only in B. And what I'll do is I'll say, all right, this is only in A, this is only in B. Let's pop off the event or the operation with the highest number. So we'll pop this one off. And this is only in B. So we pop it off, and then we add all of the parents. So we'll say 33 is also only in B. And that's not quite right, but we'll fix it soon. Then we pop the next thing with the next highest item off, which is going to be 34. And this is going to be only in A. So we pop that off, and then we look at its parents. Now, its parent is this 33 item, which is already marked as only in B. And if something is both only in B and also in A, that means it's a shared thing. So we'll say, oh, well, that means that 33 is shared between both paths. Now, if we're ever in a state where everything in the priority queue is shared, that means that there's nothing else that we're ever going to omit, even if we search the entire tree, which is only in A or only in B. And that's all that this diff function is really trying to do. We're trying to get a list of all of the only in A things and a list of all of the only in B things. So we can stop at that point. So to manage that, I'm going to have a const flag. So we've got this diff flag if something is in A or it's B or it's shared. And then let's just have a map from local version to the diff flag. So we can store what the diff flag is for every single local version. And also let num shared equals 0. So if we are ever in a situation where the number of shared items is the same as the length of the queue, then we can immediately stop because we're done. I'm going to make a little internal function, function enqueue, which is going to take some version and a flag, and it's going to actually like queue v with the specified flag. I mean, I guess it's kind of obvious. Now you think that what I'd want to do is say queue.enc v and also flags.set v flag. This is what I want to do most of the time. But remember this case where I'm popping off 34 and then I want to enqueue 33, and 33 is already in there with a flag of only B. So I want to then say, well, if it's already got B and I'm adding it as A, then really it should be a shared item. So let's write the logic for that. Flag equals flags.get v. If old flag is not null, so if old flag exists, oh, and by the way, if the flag already exists, that also means the item's already in the queue. So we don't really have to enqueue it. If it is null, we'll do all this stuff. So this is just the kind of normal path. But if it's not null, and if old flag is not equal to the flag that I'm adding now, then flags.set for v, now we're going to be diff flag.shared. Oh yeah, and also num shared plus plus. So if we add, anytime we add something shared, we need to say that num shared goes up by 1. And if we pop something off which is shared, we need to decrement it. And generally, we're just going to enqueue the item and set the flag to be whatever the flag passed in is. So then for AA of A, we can enqueue A with a flag of diff flag.a, and we can do the same for B. Great. And of course, if there are items like that are already in both of them or something, then this will do the right thing because we're already immediately going to set things to be shared if we need to. So now we're ready for our loop. I'm just going to make some arrays. So const only, or A only is a list of local versions, and B only is a list of local versions. And then, and they're both empty lists. And when we get to the end of the function, we're going to return A only and B only, because that's the return value that we specified. Okay, so now we're ready to go through our queue. So while queue.size is still greater than num shared, which is to say that there are things in here which aren't actually shared items, then let's pop off the one with the highest local version, add that to our lists if we need to, A only and B only, and then add all of the parents back to the queue, and then just keep on going. So eventually we're going to either traverse the entire graph and get to like an empty queue, or we're going to find some shared version such that everything in the queue is shared, and at that point we can stop because we know that there's nothing else that's common between both of them. So this is then pretty easy. So const lv equals q dot dq. Const flag equals flags dot get the local version, and that's definitely going to be in flags because we only add things when we add things. We always add it to the flag set. I could even delete it out of the flags map, but it doesn't really matter. If the flag is shared, then the number of shared things drops by 1. Else if the flag is diff flag dot a, well, if it's that means it's only an a. So a only dot push lv, and else if the flag is b, then b only dot push. So I'm visiting something. If it's got a flag of only a, we add it to a's. If it's b's, we add it to b's. If it's shared, then we reduce the number of shared things in our queue because it's not in the queue anymore. Finally, I need to sort of recurse or iterate. So we need to add all of the parents of this item. Otherwise, we'll just stop immediately. Remember that our tree could look like this. I'm going to reset it. We could have something like this where, and if we're comparing 2 and 6, so we're comparing this and this, we actually want to say that 6, 5, 4, and 3 are all in the like only this side, and 2, 1, and 0 are all in the only this side spot. Here, nothing is shared. And when we finally get to the top here, well, root, remember, is just empty parents list. So we won't stop until the queue itself is actually empty. So I guess we've got the op, which is oplog.ops at that version. And then for const p of op.parents enqueue p with the flag, which is the same flag that its parent got. So that's done. Notice that this function is a bit longer than it was before, but I hope it's not crazy. Like, here's the old implementation, and here's the new implementation. The main difference here is that this function knows when to stop. So if we've got a bajillion changes, and there's only some small changes right at the end, we don't have to actually expand the entire tree all the way up, like the entire graph, to be able to figure out what the change is. Let's see if it works. Fuzzer. Oop, priority queue is empty. What did I do wrong? I know what we did wrong. The bug here, and it's absolutely not obvious, is that in the case when we're enqueuing a new item, so the flag is null, but so the old flag is null, but if the new flag is shared, then in this case we also need to say num shared plus plus past end of items list. But the fact that it worked before means that it's probably a bug in our diff function. So I'm going to use the tried and true debugging method of print statements. Diff a b. I found the bug by staring at it. So the bug is here. If old flag is already shared, so we're already storing shared in our flags, but I'm being passed in like a flag of only a, then in that case, we actually don't need to set the flag or because it's already shared, but also we don't want to increment num shared. This is a bug just here. So it's sort of like if old flag is not flag and old flag is not equal to diff flag dot shared, then we want to do this. Yay, and now it's working. Great. So I'm just going to clean up this logic a little bit. I don't really like all these different comparisons of flag. We can sort of simplify. So I'm just going to say, if old flag is null, then we'll do this. Else, if, then we'll do this. Is not equal to diff flag dot shared. And let's see how we go. I mean, look at that. That is so much better. That's exactly what it should be doing. So now we're burning through all of these seeds, and yeah, look how much faster our algorithm is running now. Couldn't be. That makes me so happy. Oh my god, that is way more dramatic than I expected it to be. All right. Okay, so this is good. So git commit replaced old bad diff function with something much better. All right, I'm going to then also delete the old function, and we also don't need this expand version to set. This is all unnecessary. removed old diff code. So the next thing that I want to do, and this is sort of the last thing I'm going to do today in this video, is we've got way down here, we've got this checkout function. So right now, every time checkout gets called, we generate the document from scratch, completely from scratch. So we start with an empty snapshot and we fill it up by generating the CRDT. A lot of the time, we're going to have situations like this where I've got some big long document. So we've got all of this stuff. And then a user makes a single change right at the end. So we've got this single edit, and I need to merge it across to add this little extra X way over here. And now they're the same. In this case, I don't want to have to actually regenerate the entire thing from scratch because it's really inefficient. So luckily there's a way that we can solve this. I've got a really horrible question in my mind, which is how much of this code to do live versus how much just to pull in. And I'm going to be a horrible human being, and I'm going to pull in some code that I've written before. So there's a couple things I want to do here. Actually, first of all, let's just tidy this up and get rid of all these console logs. All right. So the interesting part of this algorithm is this. Right now, so far, what we do is we generate a CRDT from scratch. And then we use that CRDT to be able to put stuff into the snapshot. What we want to do instead is, so there's two optimizations that I want to make. The first one is I want to have some new checkout function. I'm just going to make a copy of this. So we've got old checkout and this old checkout, and then this is new checkout. Just going to call this, checkout fancy. What I want to do is have a function which takes a snapshot, which is our existing snapshot, and the snapshot exists at some version. And I want to then update the snapshot to change this snapshot into the snapshot that it should be after these new changes have been applied. So again, for now, let's make it so that we're going to merge in everything in oplog that's not already in snapshot. So one of the problems we run into is this CRDT document state. We really need a CRDT document state which contains a bunch of items for us to be able to merge in changes. Like for example, so let's say I've got this document state and I want to merge these two together. So the document on the left, we already know that the document state contains a string with A in it. But to be able to merge this B item in, we need to run that integrate function, which remember needs to have an item corresponding to B and compare it to the item corresponding to A to see which way around these two inserts go. So for that, I need the CRDT document state for this document on the left to be able to do the merge. There's a few ways to do this. One way would be that we could just store the most recently generated CRDT state and then just reuse that every time. The downside with that though is we go back to having that problem of CRDTs, that we're storing this potentially very large in-memory data structure, which represents every single change that's ever happened, just to be able to do a merge. And I don't want to have to do that. And thankfully we don't have to. But let's just start with that. The other thing I want to do, and this is a bit hard to describe, is that I want to first of all figure out what this CRDT document state looks like when this snapshot was generated. So again, I'm not going to cache it, but I'm going to regenerate it in its entirety for now, and I'm going to show you how to decrease that soon. So we'll generate the CRDT document state corresponding to this snapshot, and after we've done that, then I want to add all of the new operations that don't exist yet in the document one by one. So this approach here won't work because what this is currently doing is going through every single operation in the oplog. What I really want to do is first of all, step one, go through all changes in the snapshot version, which we're calling frontier. And then for step two, I want to add all other operations. When I do step one here, I'm kind of ignore the snapshot object itself. We've already got a snapshot that was created at this frontier version, so we don't need to regenerate it. And then in step two, now I'm going to modify the snapshot. So that's my broad approach. So the first thing I'm going to actually do, as strange as it might be, is I'm going to take all of this stuff and I'm going to move all of this out into a separate function. So I guess function do one operation, I don't know, and we're going to do all of this stuff. So we get the operation out of the oplog. We're going to grab the difference. Oh, we're also going to need the document itself. So So we grab the operation, we'll find out the difference between the current version of the document and the operation's parents. Then we retreat if we need to, we advance if we need to, we apply it to the snapshot, and then we modify the current version. I'm also going to pass in the snapshot here, oops, as a t or null. So in the first phase of this algorithm, when I'm going through all the changes that are in the snapshot version already, that are already in this, I'm going to pass null for the snapshot, which means don't modify any document state itself. And I need to kind of ripple do this. So this apply function also needs to take snapshot or null, and it's probably going to complain. So if snapshot is not equals to null, snapshot.slice. Integrate as well. So integrate's going to take a snapshot or null. Remember, integrate does a bunch more things than just edit the snapshot. So we're still going to have to call it even if the snapshot's null. But if the snapshot is null, if snapshot is not equal to null, if the snapshot is null, then we do everything just the same. We just don't do this final splicing into the snapshot object. So now our function can take an optional snapshot. Now we can say, we can change this to do one operation with all of this stuff. And this should be unchanged from how it was before. All right, so we've got this oplog version, and the oplog contains a whole lot of operations. The next thing I need to do is split the set of operations into two buckets. One way I think about it is this kind of Venn diagram. Like imagine we've got all of the operations that are in the frontier, so in this frontier set, and then we've got all of the operations that are in the operation log. What I want to do is separate them out and get back a list of everything in the frontier as one set, and secondly, a set of everything that's in the operation log, but not in the frontier set. And then what we'll do is we'll do this loop. So we'll say like, for, you know, if it was like const, let's call them like the snapshot ops, some list. So for const lv of snapshot ops, this is going to be a local version list. Then we do that operation, but we pass null in as the snapshot. And essentially, remember, because we're not modifying the snapshot, what this is going to do is regenerate this document, the CRDT document, at the state that it should be in at this frontier version here. And once we've done that, then I'm also going to have some second list, which is all of the like new ops. And I'll do the same thing as this. So for LV and new ops, I'm going to do that operation, and I'm going to also actually apply it to the snapshot. So this is fundamentally our algorithm, but we need both of these lists. So the first version of this, I'm going to use the same approach we used for our old diffing function. So I think I actually deleted that diffing function too soon. So let's bring it back. So the old version did this. We had this expand version to set function, which took in an operation log and a frontier and gave us the set of all operations. So in a sense, the snapshot operations is equal to the expand versions to set from oplog and frontier. And we want this as a list. And then the new operations is going to be, actually, let's do it like this. So const snapshot ops as set is that. So here I'm going to store the set. The new operations that we're adding is just everything in oplog minus all of this stuff. So this will be, I guess, expand versions in set from oplog and from oplog.frontier, which is the set of all changes in the oplog, dot difference. So subtract out everything in here. And then I want it to be a list. So now if I run this, I think it should work. So our new checkout fancy function can take in an oplog, an existing snapshot, and a frontier. Let's actually change our code to use it. So right now we're using this checkout function here and there. So I'm going to leave the check function alone. I think this is totally fine. But let's modify this merge from. So I merged everything from this other version into the local oplog, into this .oplog. And after that, instead of replacing snapshot with checkout, with this new checkout, I'm instead going to say checkout fancy. So we've got an operation log, this .oplog. We've got a snapshot, and we want the current frontier. Well, let's do it like this. We've got our snapshot, and I'm also going to store the sort of current like frontier, which is the version that this snapshot is at. This dot frontier also equals empty list. So when I insert, I also need to modify the local frontier that we've got here. And when I call insert, I'm going to be inserting something into the oplog. So local insert's going to modify the oplog's frontier to be the set of all changes. So I can just say this dot frontier equals oplog dot frontier. This dot oplog dot frontier. I'm going to slice, which will make a shallow clone of it. This is all a bit dirty. I'll clean this up in a bit. And when we reset, we'll also say this dot frontier equals empty list. So now check out fancy. So we've got the current snapshot, and we've got this snapshot at this particular version in time. And every time we make a change, I modify this dot frontier. Now, in this merge from function, the oplog's frontier has been modified, but our local frontier hasn't. So check out fancy will then also take this dot frontier as like the version that our snapshot's at. And then this dot frontier again is going to be like, let's just copy it out from the oplog. I think these slices might actually be unnecessary now I think about it, but I like it like this. Okay, does it work? No, but it doesn't work like that. Oh, these operations have to be done in order. So, actually I'm just going to do it in line. This is kind of dirty, but sort LVs of that. And new ops is sort LVs of that. There we go. And now it's working using our fancy new snapshot checkout function. Using checkout fancy. So you might notice that it's not really much faster. And the reason for that is that the only work that we're not doing now is modifying the snapshot, like creating the snapshot as we go through the first part of the document. But we can actually do much better than that. And let me tell you how. So there's this trick which Eggwalker takes advantage of to be able to be efficient, you know, in the proper versions of Eggwalker, where it turns out we don't even actually need this entire CADT document. If we think about this document structure, we've got this list of items. And let's go back to this. So this is a like standard fugue, and we can see all of these items in this list. Now, each of these items has this origin left and origin right properties, which are quite important to know that if there's two inserts that both happen exactly at the same location, then we can figure out what order those two inserts should happen. So in this document, if I type an X here, and I find the same location in the document on the right, and I type a Y there, then if I merge both of these changes, that X and Y end up in the same order in both computers. And this is super important. And in some ways, this is sort of the most important thing that all of this origin right, origin left nonsense does. In a CRDT, we need to keep around all of this stuff because we never know when another change is going to come in. It could be that, you know, your friend Carol might have gotten on a plane and she had a laptop open and she had a document open and she typed a bunch of stuff. And 3 weeks later, she comes back from holiday and she opens up her laptop. And when she does, all of the changes that are in her local document state need to merge with everyone else's documents. And when that happens, who knows? Who knows where she typed? She could have typed right here where the X and Y is. And if she did, then we need to keep around the D and the A so that we can figure out, like, we can look up these origin left and origin right positions and insert in the right location. But Eggwalker has a little trick. We've got this sneaky thing that we can do. Because we have the entire operation log that we're merging locally in memory, we can skip entire swathes of the CRDT. We can skip whole parts of it because I know that none of the items inside this origin left, origin right could matter. And let me be more specific about this. So I'm going to go back to my Eggwalker implementation. Let's say I have a giant list like this, and I've got two document states that both have all of these changes. Now, right at the end, we make some changes. So right down here, I do this merge. Now, if I have, let's say I'm at this document state 47, and I want to merge this change 48 in. It turns out that all of the CRDT items corresponding to 46 all the way back to the start don't actually matter. The origin left and origin right are completely ignored. The only thing that could affect the position of this item inserted at 48 is this item inserted at 47. And the reason that it could be affected, I mean, obviously, first of all, they can be affected because they're inserted at the same position. But more importantly than that, and that's actually quite a difficult property to check generally, it could affect it because these changes are concurrent. If I've got two changes and one happens sequentially after the other, it's impossible that we're going to have to use the integrate function to figure out how they're ordered. The users ordered them because they saw that change and they put their cursor either on the left-hand side or the right-hand side of the other user's change. So because of this, we can actually do something much, much cleverer in our checkout fancy code. What I'm going to do is I'm going to generate a CRDT that corresponds to what the document looked like at the most recent common version between this Frontier version and our resulting oplog. Going back to this state, if I was merging these two changes together, I was at 47, I'm merging in your change at 48. What I need to do is find version 46, which is the most recent common version, and generate kind of a dummy CRDT structure corresponding to version 46. Then the only changes I need to look at is this change 47 to add it to our CRDT properly, and change 48 to be able to do the insert. We don't even have to read anything above this. None of this stuff matters. We just generate a dummy object and we can do this merge directly without looking at any of that stuff. So I'm going to show you what that looks like. But first of all, I'm going to pull in a function that is kind of horribly complicated. So I'm pasting in some code. This is about 100 lines of code. What I've got here is this new function called find difference. And what it does is, I feel like this is the wrong name for it. I don't know. What we're going to do is output the common version. So this is going to be, say in this case, the common version will be version 46. The second thing I'm going to output is this sort of shared operations. So remember, I'm going to start at version 46 and version 47 is a shared version, which it doesn't look like it should be shared, but bear with me. So I'm merging from version 47 and I want to add this version 48. What I'm really doing is merging from version 47 to the result is versions 47 and 48 put together. So this version 47, it's included currently in the snapshot version, and it's going to be included in the resulting version. And importantly, I need to add it to my local CRDT because this change here is concurrent with it, which means that the CRDT actually matters for this change in particular. For anything earlier than this, the CRDT doesn't matter. So that's what our shared ops is. And the be only ops is going to be just the things that we need to add. So just this operation 48. So I'm calling it a difference. That's a really bad name. God, what should we call it? Like ops to look at. I don't know. Say something in the comments if you've got a better idea of what this type should be. But importantly, we've got a common version, shared ops, and be only ops. Now this find difference function, which returns this, I guess maybe I should call it like, find ops to visit. Actually, maybe that's better. Ops to visit. What this function will do is we take in A, which is the version 47, and B, which is the resulting version after everything's merged. So in that case, it's the combined version 47 and 48. And it's going to return this thing, which is what the most recent common version is, the shared operations, and what things are only in the things that we need to add. The internal logic is quite complicated. It's, it's not that bad. It's quite similar to the diff function that we had above, but with an extra wrinkle, which is you can have situations like this where I have A and B, then we merge them. Then I can have C and D and we merge them. And we can have a version like this. In this case, when I merge versions 2 and 3, there is actually a common version. The common version is the merger of 0 and 1. So this little merge dot here is the common version that we want to stop at. So we want to generate a dummy CRDT at this little point here, and then that way we can merge all of this stuff together correctly. But unfortunately, we don't have a single local version number that represents this merger. So as a result of that, this code ends up being a bit more complicated, where we have these merge points that describe a list of versions, and then we've got to be able to compare them and blah, blah, blah. But take my word for it that it works, and you can have a read through it yourself if you're interested in how it works. Once we've got that, then we can make this checkout fancy function work a bit better. So the first thing I want to do is I'm going to call that const blah equals find ops to visit. So in our oplog, we've got the frontier, and we're going from the frontier version to the oplog.frontier. And this is going to then return the common version, the shared operations, and the be only operations. I'm generating a document. This document states, this is our CRDT. I'm actually going to populate it with a bunch of junk to start off with. So the problem is that we actually need a sort of dummy item for everything that's inside this document at the common version, which is really annoying. So the current version is actually going to be the common version. So again, going back to this, the common version is going to be this merge point here. And I'm going to have to put some crap into this items list and, and sort out the items by LV. So I'm just going to make a bunch of junk and put it in here. So I'm going to call these placeholder items. So const placeholder length. I need a placeholder length such that if you choose to delete any item that's inside the snapshot or from this common version, if anything in that entire document gets deleted, then the CRDT, so this list of items, is at least that long. But I don't actually know how long the document was at that common version. So we can be a bit conservative. I found that this works. If I say the maximum local version in the frontier version and add 1 to it, then this seems to work. And the fuzzer seems happy with it. So I'll go with this. You might think that it's a pain in the ass needing to add a whole bunch of junk here. And you're right. If you use run length encoding, so some algorithms, I think I mentioned it earlier, some implementations of this will use internal run length encoding, so that this items list, every single item in here actually represents a run of items where the local versions are sequential. And in that case, we can just insert one single item for the placeholder, which actually internally contains a bajillion placeholder items. And then we don't need these horrible hacks. But I'm going with it for now. For let I equals 0, I is less than placeholder length, I++. Const item is a CRDT item, which equals this. So I'm going to make this some junk. The LV is going to be I plus, 1E12. So this obviously isn't a real local version, but it actually doesn't matter. The current state is inserted. It doesn't matter about things that have been deleted before that point in time. It's actually totally irrelevant to the algorithm. Deleted's false. The origin left is -1, and origin right is also -1. And that's totally fine. Doc.items.push our new item. I'm also going to say doc.items by LV for this item is item. And this is kind of horrible. I'm being really mean to JavaScript by making this local version such a big number and then trying to use that as an index in a list. But modern JavaScript seems totally fine with this sort of hijinks. If it worried you, you could probably replace this items by LV thing with, you could make this instead of like a map from LV to CRDT item. I'm just using a list because I'm lazy. So that'll add a bunch of placeholder items. And then after that, down here, we actually don't need to change much. So I don't want this new ops stuff. So I'm going to use the shared ops and be only ops that came in from our find ops to visit function. So this is shared ops, and this is be only ops. And thanks to the magic of this wild choice to have this placeholder thing, these are the only operations we actually need to look at. Let's see if that works. And there we go. So now we're actually doing incremental changes. Let's actually print out what the difference is here. So we visited shared ops.length plus b only ops.length, and total. So the total number of operations is oplog.ops.length. And let's see how that compares. So look at these numbers. We visited 9 operations. There was 265 operations in the oplog, but we only need to manage 9 of them. We visited 0 operations. We had 257 total operations, and a naive version of this algorithm would have had to add 257 operations to our CRDT structure. We added none of them. And you can see as we go back, the number of visited items is far smaller than the total. In general, if this algorithm is implemented correctly, this is the kind of behavior you should expect, where the number of items we actually visit is going to grow in proportion to the distance between the changes. So it's the number of changes back to the shared fork point, and then, both arcs on both sides. And that is our fancy checkout function. So that brings me to the end of the coding section. Well, sort of. I'm going to do one little thing just to clean this code up a little bit, which is going to make me really happy. It's been bothering me for the last 20 minutes. But otherwise, this is a totally working, totally consistent and coherent version of Eggwalker. Let me delete this expand version to set thing again, because I hate it, and I hate that it exists. And now we only have these efficient algorithms. We've got our find ops to visit, and we've got our diff function wherever it is. And we've got this fancy checkout function. We've also got our simple checkout function up here. Yeah, this is our simple checkout function. I am going to replace all of this with calling, what was it, do one or something, do one operation, doc, oplog, lv, and snapshot. So I had all of this code that I copy and pasted into this do one operation function here, but I hadn't actually removed it from above. The other thing I'm going to do is I'm going to add a structure for a branch. So export type branch. So in Git, we don't always work off the head. So we don't always use the most recent version, which contains every single change merged in. And that's equally true in any other editing situation. One of the reasons why I care a lot about this stuff is I look at other people who aren't programmers, and the poor souls are using tools that aren't as good as Git. And we've known how good Git can be for years, but we've been selfish jerks, and we haven't shared that technology and those ideas with anyone else. So I'm going to invent the idea of a branch here. And a branch is a snapshot. I guess it's a branch with some type. A branch is a snapshot, which is a document at some point in time, and it's got a frontier. So the frontier is the version of this branch. And now it's way less confusing. So this checkout fancy function can take a branch of t. Find ops to visit, oplog, branch.frontier, oplog.frontier, max of branch.frontier, and this is the branch.snapshot we're modifying. Oh yeah, also when we're done, the resulting version, so remember that we've got this CRDT document that stores the current version. Oh, actually, no, it's okay. I was going to say, we need the branch to finally also contain the resulting document version. So there's one more change I want to make. So in the branch, we've modified the snapshot, but I also want the resulting frontier to line up with the snapshot that it now contains. So I'm going to add one more line here, which is advance frontier. So remember, this is the part where we're actually adding new operations into the branch. So I'm going to modify the branch.frontier to add the local version, and the parents is oplog.ops at lv.parents. So this is going to make it so that the branch's frontier is automatically up to date after this function's run. Then down here in CRDT document, I can replace both of these with a branch. I guess for consistency, I'll make a function create branch. It's going to return a branch at some t. Create branch. Then in our check function, we can still use the same checkout code. This dot branch dot snapshot, I guess. The insert function. So if we wanted to, we could take this code and make a branch local insert function, which would do all of this work. I'm going to leave it longhand here. It'll be branch.snapshot and branch.frontier, but it would be better to take both of these lines, actually maybe all three of these lines here, and put them into some sort of local insert into branch function. And likewise here, branch.snapshot, branch.front. GetString is going to turn branch.snapshot.join. Merge from is going to check out fancy, and we're going to pass in this.branch, and we don't need to modify the frontier. And reset then is also going to just say that. Great. Okay. And that's pretty good. So one last change to the code, just for cleanups, is that this checkout fancy function currently merges everything in oplog into the branch, but that's not necessarily what we want. So I'm going to add another field here, which is merge frontier. So this is sort of like the frontier that I want to merge into my branch. And by default, this will just be the oplog.frontier, but we could specify a different version if we wanted to. And this is going to let us, let's say we've got an oplog with a whole bunch of stuff. I could create a new branch and then like check out into my branch at some earlier version in time that doesn't include everything to see what the document looked like at an earlier point, or have tags or have anything else like that, the kinds of things that Git has. And this function actually just doesn't need to change much if I do this. So now when I go find ops to visit, I'm actually just going to pass in the merge frontier. And I think everything else is the same. Okay. So that is Eggwalker. I'm just going to rerun the test to make sure it's not broken. Oops. Oh yeah, my fuzzer is broken because it's using doc.snapshot directly. Oops. The thing that I forgot is advanced frontier returns the new frontier. It doesn't actually modify a frontier in place. So branch.frontier equals, I don't know why Z does that. So now it's running much faster. And now at this point in the fuzzer, I'm going to get rid of this sort of more paranoid check. And we can see it blasts through all of those changes. So this is way faster than it was before. Should be able to also bun run build. And we're going to get a slightly larger JavaScript bundle. But now, if I refresh this, it's using all of our new fancy code. And the only things that are being changed in the snapshot is whatever was changed. Wow. Okay, so that was a massive marathon. If you've made it through all 4 hours of me talking, or thereabouts, I hope that this edits down a little bit at least, then congratulations. You now understand something that probably less than a couple dozen people on the planet understand, which is the mad mind behind all of this wild, oops, not that code, Eggwalker, and how Eggwalker works. I hope it's not too complicated. I mean, it's one of these algorithms where sort of once you understand it, I think it sort of makes some sense. It's got a few little thorny edge cases, but we've ended up with what, like 590 lines. So, you know, if I don't include the little wrapper, we've got 540 lines of code. And this is code that will make any real-time collaborative text editor work incredibly well and be able to work in a way that's sort of best in class. If you want to save stuff to disk, all you have to do is save this oplog and all the items inside it, and sending things over the network, again, is just saving this oplog. Everything else is taken care of by the merging and by the fancy merging. And as I say, this algorithm allows you to be able to, you know, have this sort of fancy branches, be able to check out what the document looks like at any point in time without needing to do any work after the fact. We've got in here, so today we added this checkout fancy. This, I think, is the most important change to the whole algorithm, which is going to mean that we can merge changes without having to actually look at all of the historical changes. We can create a CRDT just from the most recent common point in time, and then merge all of the changes that have happened since then. There's a few optimizations that Eggwalker supports, which I haven't implemented in this implementation. So one is obviously run length encoding. Another one is fast forwarding. So I showed the retreat, advance, and apply operations or actions. There's another one that I actually use in diamond types, or two more. One is called fast forward, another one's called clear. So right now, every time we apply an operation, we're always doing this apply, which modifies the CRDT structure. A lot of the time you have situations like this where there's actually no concurrency. And in this case, we don't even need to modify the CRDT at all because I know that this change is not concurrent with anything else that I'm going to end up merging. So in that case, I can actually just take these changes, take these operations, and apply them directly to the snapshot without even bothering having to sort out the CRDT structure. Now, if I've got a big long list here, and then I've got some little diamond or something down here, we will have to create a dummy CRDT structure at that diamond, but it's kind of something that we can sort out later. So in diamond types, if I've got, let's say I've got something like this, and then I've got a bunch of changes, and then I have this. So I've got some little diamond here. Then I've got a bunch of stuff that's not concurrent with anything, and I've got another diamond. Then the best implementations of Eggwalker can apply this, clear the CRDT, replace it with some placeholder, apply all of this stuff in the middle just directly to the snapshot, then create a new placeholder just after this version, and apply both of these using the fancy CRDT structure. And this gets you like another many-fold optimization or performance improvement on the original. But this is the summary, and I'm throwing new information at you, so I'm sorry. But I think that we should be really happy with this. This is a really good implementation, and it's a good implementation of Eggwalker, which is quite a fancy algorithm. I'll obviously post all of this. I'll put it up on GitHub. So if you want to have a bit of a read yourself, you're more than welcome to. And there's obviously a bit of code here, but I hope that none of it is too complicated that you can't make heads and tails of it. I mean, I say that while scrolling over the integrate function, which is probably the trickiest of all. Today we also added a fuzzer. So the fuzzer lets us find out whether or not we've made any mistakes without having to find out with our face. And we optimize the fuzzer from the very first version to be able to run this fast. So every time it goes up by 1, we've run 100 iterations of making lots of random changes to a document, merging, doing all sorts of wild stuff. And we can still burn through seeds this fast, which is really great for JavaScript, especially given we haven't done that much work optimizing. So I'm really happy with that. And I've also shown you how to have like a dot output. So this little tool will let you be able to noodle around and get graphs like, just like mine, when you're making changes and noodling around. I'll post this online somewhere, like my little version of it, which puts these little graphs inline in the web browser, just because I think it's a really good tool to be able to understand what's going on. It'd be even better if when we did the fancy merging, I could sort of color code all of these boxes by like what's the common stuff and what are we adding and what are we changing. But yeah, but I hope at least this gives you a sense of how Eggwalker works. If you want to obviously read the paper, and it shouldn't be that confusing once you know the algorithm itself. We've got the same like graphs of events. We call them events inside the paper instead of operations, but it's exactly the same concept. We've got the same set of states. We've got the same retreating and advancing with this SP and SE. So SP is the state, the present state, and SE is the end state. So SE is just our deleted variable, which marks whether or not something was ever deleted. So it goes from insert to delete. And SP is that extra state variable saying what the state is right now. And I've also done some really extensive benchmarking work. So we can see how it stacks up compared to different algorithms in a whole bunch of different cases, including YJS. So I find this really interesting where in this C1, C2 examples, this was like 2 users typing literally at the same time, with some inserted latency. And in Eggwalker, because we store the relative time when every single change happened to every other change, we end up being like needing more disk space than YJS does, which throws out that information. YJS can't actually reconstruct the document state at any given point in time because it doesn't store enough information to do so. But in other cases, Eggwalker is actually really small. And this is some examples from Git. This is some examples which are purely sequential editing traces. And here this light shaded bit is just the pure text, like what was actually typed. And this is the tiny bit of overhead of metadata that we need to store to be able to make Eggwalker, the entire algorithm, work. Yeah, and I'm really happy with this. This is with and without some optimizations. So you can see that I was talking about that fast forwarding. So if we enable fast forwarding, these purely sequential traces become like sort of, about 5 times faster than they were before. The other traces don't change by much, and that's pretty cool. And yeah, and generally I'm really happy with it. Have a read, have a code, have a play around. As I say, diamond types is the if you want to look at what the big boys version of this code looks like, you're welcome to, but it's absolutely not needed. And this is the core algorithm that I hope will be able to power the Google Docs applications of the future. So again, I'll shut up. Thank you so much for watching. Thanks for sticking with it. And I'm really keen to see what everybody who watches this video ends up doing with this algorithm, because as I say, I think it's pretty cool. Yeah. Okay. Bye.